In computer programming, a string is traditionally a sequence of characters, either as a literal constant or as some kind of variable. The latter may allow its elements to be mutated and the length changed, or it may be fixed. A string is generally understood as a data type and is often implemented as an array of bytes that stores a sequence of elements, typically characters, using some character encoding. A string may also denote more general arrays or other sequence data types and structures, depending on programming language and precise data type used. A variable declared to be a string may either cause storage in memory to be statically allocated for a predetermined maximum length or employ dynamic allocation to allow it to hold variable number of elements. When a string appears literally in source code, it is known as a string literal or an anonymous string. In formal languages, which are used in mathematical logic and theoretical computer science, a string is a finite sequence of symbols that are chosen from a set called an alphabet. Formal theory. Let sigma be a non-empty finite set of symbols, called the alphabet. No assumption is made about the nature of the symbols. A string over sigma is any finite sequence of symbols from sigma. For example, if sigma equals 0, 1, then 01011 is a string over sigma. The length of a string S is the number of symbols in S and can be any non-negative integer. It is often denoted as S. The empty string is the unique string over sigma of length 0, and is denoted epsilon or lambda. The set of all strings over sigma of length n is denoted sigma n. For example, if sigma equals 0, 1, then sigma 2 equals 00, 01, 10, 11. Note that sigma 0 equals epsilon for any alphabet sigma. The set of all strings over sigma of any length is the clean closure of sigma and is denoted sigma asterisk. In terms of sigma n, for example, if sigma equals 0, 1, then sigma asterisk equals epsilon 0, 1, 00, 01, 10, 11,000, 001, 010, 011. Although the set sigma asterisk itself is countably infinite, each element of sigma asterisk is a string of finite length. A set of strings over sigma is called the formal language over sigma. For example, if sigma equals 0, 1, the set of strings with an even number of zeros, epsilon, 1, 00, 11, 001, 010, 100, 111, 0000, 0011, 0101, 0110, 1001, 1010. 1100, 1111, is a formal language over sigma. Concatenation and substrings. Concatenation is an important binary operation on sigma asterisk. For any two strings S and T in sigma asterisk, their concatenation is defined as the sequence of symbols in S followed by the sequence of characters in T, and is denoted street. For example, if sigma equals A, B, Z, S equals bear, and T equals hug, then Saint equals bear hug and TS equals hug bear. String concatenation is an associative but non-commutative operation. The empty string epsilon serves as the identity element for any string S. Epsilon S equals S, epsilon equals S. Therefore, the set sigma asterisk and the concatenation operation form a monoid, the free monoid generated by sigma. In addition, the length function defines a monoid homomorphism from sigma asterisk to the non-negative integers. A string S is said to be a substring or factor of T if there exist strings U and V such that T equals USV. The relation is a substring of defines a partial order on sigma asterisk, the least element of which is the empty string. Prefixes and suffixes. A string S is said to be a prefix of T if there exists a string U such that T equals SU. If U is non-empty, S is said to be a proper prefix of T. Symmetrically, a string S is said to be a suffix of T if there exists a string U such that T equals S. If U is non-empty, S is said to be a proper suffix of T. Suffixes and prefixes are substrings of T. Both the relations is a prefix of and is a suffix of are prefix orders. Rotations A string S equals UV is said to be a rotation of T if T equals VU. For example, if sigma equals 0, 1, the string 00110001 is a rotation of 01001110, where U equals 00110 and V equals 01. Reversal. The reverse of a string is a string with the same symbols but in reverse order. For example, if S equals ABC, then the reverse of S is CBA. A string that is the reverse of itself is called a palindrome, which also includes the empty string and all strings of length 1. Lexicographical ordering. It is often useful to define an ordering on a set of strings. If the alphabet sigma has a total order, one can define a total order on sigma asterisk called lexicographical order. For example, if sigma equals 0, 1, and 0 less than 1, then the lexicographical order on sigma asterisk includes the relationships epsilon less than 0 less than 00 less than 000 less than 0001 less than 001 less than 01 less than 010 less than 011 less than 0110 less than 01111 less than 1 less than 10 less than 100 less than 101 less than 111 less than 1111 less than 11,111. The lexicographical order is total if the alphabetical order is, but isn't, well-founded for any non-trivial alphabet. Even if the alphabetical order is. See shortleg for an alternative string ordering that preserves well-foundedness. String operations. A number of additional operations on strings commonly occur in the formal theory. These are given in the article on string operations. Topology strings admit the following interpretation as nodes on a graph. Fixed-length strings can be viewed as nodes on a hypercube. Variable-length strings can be viewed as nodes on the KARY tree, where K is the number of symbols in sigma. Infinite strings can be viewed as infinite paths on the KARY tree. The natural topology on the set of fixed-length strings or variable-length strings is the discrete topology, but the natural topology on the set of infinite strings is the limit topology. Viewing the set of infinite strings as the inverse limit of the sets of finite strings. This is the construction used for the p-adic numbers and some constructions of the Cantor set, and yields the same topology. Isomorphisms between string representations of topologies can be found by normalizing according to the lexicographically minimal string rotation. String data types. A string data type is a data type modeled on the idea of a formal string. Strings are such an important and useful data type that they are implemented in nearly every programming language. In some languages they are available as primitive types and in others as composite types. The syntax of most high-level programming languages allows for a string, usually quoted in some way, to represent an instance of a string data type. Such a metastring is called a literal or string literal. String length. Although formal strings can have an arbitrary length, the length of strings in real languages is often constrained to an artificial maximum. In general, there are two types of string data types. Fixed-length strings, which have a fixed maximum length to be determined at compile time and which use the same amount of memory whether this maximum is needed or not, and variable-length strings, whose length is not arbitrarily fixed and which can use varying amounts of memory depending on the actual requirements at runtime. Most strings in modern programming languages are variable-length strings. Of course, even variable-length strings are limited in length by the number of bits available to a pointer, and by the size of available computer memory. The string length can be stored as a separate integer or implicitly through a termination character, usually a character value with all bits 0. See also, null terminated, below. Character encoding. String data types have historically allocated 1 byte per character, and, although the exact character set varied by region, character encodings were similar enough that programmers could often get away with ignoring this. Since characters a program treated specially were in the same place in all the encodings a program would encounter, These character sets were typically based on ASCII or EBCDIC. Logographic languages such as Chinese, Japanese, and Korean need far more than 256 characters for reasonable representation. The normal solutions involved keeping single-byte representations for ASCII and using 2-byte representations for CJK ideographs. Use of these with existing code led to problems with matching and cutting of strings, the severity of which depended on how the character encoding was designed. Some encodings such as the UC family guarantee that a byte value in the ASCII range will represent only that ASCII character, making the encoding safe for systems that use those characters as field separators. Other encodings such as ISO 2022 and Shift-JIS do not make such guarantees, making matching on byte codes unsafe. These encodings also were not self-synchronizing, so that locating character boundaries required backing up to the start of a string, and pasting two strings together could result in corruption of the second string. Unicode has simplified the picture somewhat. Most programming languages now have a data type for Unicode strings. Unicode's preferred byte stream format UTF-8 is designed not to have the problems described above for older multibyte encodings. UTF-8, UTF-16 and UTF-32 require the programmer to know that the fixed-size code units are different than the characters. The main difficulty currently is incorrectly designed APIs that attempt to hide this difference. Implementations. Some languages like C++ implement strings as templates that can be used with any data type, but this is the exception, not the rule. Some languages, such as C++ and Ruby, normally allow the contents of a string to be changed after it has been created. These are termed mutable strings. In other languages, such as Java and Python, the value is fixed and a new string must be created if any alteration is to be made. These are termed immutable strings. Strings are typically implemented as arrays of bytes, characters, or code units. In order to allow fast access to individual units or substrings, including characters when they have a fixed length, a few languages such as Haskell implement them as linked lists instead. Some languages, such as Prolog and Erlang, avoid implementing a dedicated string data type at all, instead adopting the convention of representing strings as lists of character codes. Representations of strings depend heavily on the choice of character repertoire and the method of character encoding. Modern implementations often use the extensive repertoire defined by Unicode along with a variety of complex encodings such as UTF-8 and UTF-16. The term byte string usually indicates a general-purpose string of bytes, rather than strings of only characters, strings of bits, or such. Byte strings often imply that bytes can take any value and any data can be stored as is, meaning that there should be no value interpreted as a termination value. Most string implementations are very similar to variable-length arrays with the entries storing the character codes of corresponding characters. The principal difference is that, with certain encodings, a single logical character may take up more than one entry in the array. This happens for example with UTF-8 where single codes can take anywhere from 1 to 4 bytes. And single characters can take an arbitrary number of codes. In these cases, the logical length of the string differs from the physical length of the array. UTF-32 avoids the first part of the problem. Null terminated. The length of a string can be stored implicitly by using a special terminating character. Often this is the null character, which has all bits 0, a convention used and perpetuated by the popular C programming language. Hence, this representation is commonly referred to as a C-string. This representation of an n-character string takes n plus 1 space, and is thus an implicit data structure. In terminated strings, the terminating code is not an allowable character in any string. Strings with length field do not have this limitation and can also store arbitrary binary data. An example of a null-terminated string stored in a 10-byte buffer, along with its ASCII representation as 8-bit hexadecimal numbers is: the length of the string in the above example, Frank, is 5 characters, but it occupies 6 bytes. Characters after the terminator do not form part of the representation. They may be either part of other data or just garbage. Rough equivalents of the null termination method have historically appeared in both hardware and software. For example, data processing machines like the IBM 1401 used a special word mark bit to delimit strings at the left, where the operation would start at the right. This meant that, while the IBM 1401 had a 7-bit word in reality, almost no one ever thought to use this as a feature, and override the assignment of the 7th bit to handle ASCII codes. Length prefixed: the length of a string can also be stored explicitly, for example by prefixing the string with the length as a byte value, a convention used in many Pascal dialects. As a consequence, some people call such a string a Pascal string or p-string. Storing the string length as byte limits the maximum string length to 255. To avoid such limitations, improved implementations of p-strings use 16, 32, or 64-bit words to store the string length. When the length field covers the address space, strings are limited only by the available memory. If the length is bounded, then it can be encoded in constant space, typically a machine word, thus leading to an implicit data structure, taking n plus k space, where k is the number of characters in a word. If the length is not bounded, encoding a length n takes log space, so length prefixed strings are a succinct data structure, encoding a string of length n in log plus n space. In the latter case, the length prefix field itself doesn't have fixed length. Therefore the actual string data needs to be moved when the string grows such that the length field needs to be increased. Here is a Pascal string stored in a 10-byte buffer, along with its ASCII, UTF-8 representation. Strings as records. Many languages, including object-oriented ones, implement strings as records in a structure like class string, unsigned int length, char asterisk text, although this implementation is hidden, and accessed through member functions. The text will be a dynamically allocated memory area that might be expanded if needed. See also string. Linked list. Both character termination and length codes limit strings. For example, C character arrays that contain null characters cannot be handled directly by C string library functions. Strings using a length code are limited to the maximum value of the length code. Both of these limitations can be overcome by clever programming, but such workarounds are by definition not standard. It is possible to create data structures and functions that manipulate them that do not have the problems associated with character termination and can in principle overcome length code bounds. It is also possible to optimize the string represented using techniques from run-length encoding and Hamming encoding. While these representations are common, others are possible. Using ropes makes certain string operations, such as insertions, deletions, and concatenations more efficient. Security concerns. The differing memory layout and storage requirements of strings can affect the security of the program accessing the string data. String representations requiring a terminating character are commonly susceptible to buffer overflow problems if the terminating character is not present, caused by a coding error or an attacker deliberately altering the data. String representations adopting a separate length field are also susceptible if the length can be manipulated. In such cases, program code accessing the string data requires bounds checking to ensure that it does not inadvertently access or change data outside of the string. Memory limits. String data is frequently obtained from user input to a program. As such, it is the responsibility of the program to validate the string to ensure that it represents the expected format. Performing limited or no validation of user input can cause a program to be vulnerable to code injection attacks. Text file strings. In computer-readable text files, for example programming language source files or configuration files, strings can be represented. The null byte is normally not used as terminator since that does not correspond to the ASCII text standard, and the length is usually not stored, since the file should be human editable without bugs. Two common representations are surrounded by quotation marks, used by most programming languages. To be able to include quotation marks, new line characters etc. Escape sequences are often available, usually using the / character, terminated by a new line sequence, for example in Windows INI files. Non-text strings. While character strings are very common uses of strings, a string in computer science may refer generically to any sequence of homogeneously typed data. A string of bits or bytes, for example, may be used to represent non-textual binary data retrieved from a communications medium. This data may or may not be represented by a string-specific data type, depending on the needs of the application, the desire of the programmer, and the capabilities of the programming language being used. If the programming language's string implementation is not 8-bit, clean, data corruption may ensue. String processing algorithms. There are many algorithms for processing strings, each with various trade-offs. Some categories of algorithms include string searching algorithms for finding a given substring or pattern, string manipulation algorithms, sorting algorithms, regular expression algorithms, parsing a string, sequence mining. Advanced string algorithms often employ complex mechanisms and data structures, among them suffix trees and finite state machines. The name stringology was coined in 1984 by computer scientist Z.V.I. Galil for the issue of algorithms and data structures used for string processing.